This is part 2 of the thermochemistry notes, and we're going to be starting with thermochemical equations. A thermochemical equation is a chemical equation that includes the enthalpy change of the reaction, which could be written as either a reactant or a product. For these types of equations, you have to write in the phases of matter for the reactants and products because solids, liquids, and gases, the phases, they affect the amount of enthalpy that you could potentially have. So I have two examples shown here. In the first example, we have sodium hydrogen carbonate, which is baking soda. You're adding 129 kilojoules, and then it breaks down into sodium carbonate, water, and carbon dioxide. In the second example, you have calcium oxide and water combining to make calcium hydroxide, which also produces 65.2 kilojoules in the end. Now, if you think about whether energy is going in or out, you should be able to figure out if this is an endothermic or exothermic process. We know endo means inwards, so here energy is going into our chemical reaction. So this one right here I would label as endothermic. Whereas the second reaction, we have energy coming off at the end. The second one would be exothermic. Over here we have the same two chemical equations, but they're written in a slightly different way. So instead of writing delta H on either side of the arrow, you could put it off to the side with either a positive or a negative sign to show that it is endo or exothermic. So here there's no sign, which is an implied positive. That means that this is an endothermic process, whereas here the negative sign shows that it's exothermic, heat is coming off in the end. So you could potentially see thermochemical equations in either format. In this example, we're going to make our own thermochemical equation based on what's here. What I would typically start with is just figuring out what the balanced equation is first, and then we can do the thermochemistry after that. So it's that we have hydrochloric acid and sodium hydroxide, and we're adding these two things together and they're going to react. So that's HCl plus NaOH. This is a double replacement reaction, or an acid-base reaction. And in that type, the hydrogen and sodium are going to switch places, so our two positive ions. So that means sodium is now going to be bonding to chlorine, and hydrogen is going to be bonding to hydroxide, making H2O. Now from here, you would balance the chemical equation. If you still need to, you could put a line down through the arrow, count up the atoms on either side. But if you add everything up, this is actually already balanced. We have a single sodium on either side, one chlorine, one oxygen, two hydrogens, and two hydrogens since they're in two different spots over here. So now that I have my balanced equation, I just need to know how much energy is actually being absorbed or emitted and which side of the arrow it belongs on. And in order to do that, I'm going to use my equation of Q equals mc delta T. So step one is going to be to pull out all the relevant information from the word equation, which is up here. Now I've mentioned this type of problem before in class. When I say that I have 75 milliliters of 1 molar hydrochloric acid, what that really means is that I have 75 milliliters of water with acid dissolved in it. The same can be said for the 75 milliliters of the sodium hydroxide. It's really 75 milliliters of water. That means that I have a total volume of 150 milliliters of H2O. And because the density of water is 1, 150 milliliters is the same as 150 grams. So that's going to be the mass that I use here. And actually, all of these numbers that I initially start off with are going to be numbers for water. Because I know the specific heat of water, I know it's 4.184 joules per gram degree Celsius. I don't know the specific heat of these other substances here. The temperature change, it's starting off at 22.5 for both of these chemicals that are being mixed together, eventually goes up to a maximum of 26 degrees Celsius. So in order to find delta T, it's final minus initial, so 26 minus 22.5, that is a difference of 3.5 degrees Celsius. So from here, I'm going to plug in all of my numbers to find QW, so that's 150.0 grams times 4.184 joules per gram degree Celsius times 3.5 degrees Celsius. So QW here, after I round it for two significant figures, I end up with 2,200 joules. And it's a positive value, which could also be written as 2.2 kilojoules. If you're not familiar with that conversion, you're basically just dividing by 1,000. Or if you wanted to set it up like a regular conversion, you can put your time sign with your line, joules on the bottom, and kilojoules on top. You end up with 2.2. All right, now that was the Q of the water. Delta H, which is the same as Q of the system, is going to be the same value, but the opposite sign. So that's going to be negative 2.2 kilojoules. Now for this number, I'm just going to kind of hold on to this until the very end, because that's how many kilojoules I have, but for this random concentration and volume of hydrochloric acid and sodium hydroxide, I want to turn it into kilojoules per mole, because that's what this delta H standard is. So in order to do that, molarity is equal to moles per liter. I know my molarity was 1 molar, and I know my volume was 75 milliliters. So if I multiply both sides by liters, I can cancel out and figure out how many moles I'm supposed to be using here. Now, I have 75, actually hold on a second. Yeah, sorry, that is 75. So I have 75.0 milliliters of the HCl. So for this part, we're not combining the two 75s for 150. We just want the individual chemicals. So for the sodium hydroxide or for the HCl, it was 75. I'm going to cancel out milliliters on my way to liters. And for 1 liter, I have 1,000 milliliters. So we're just dividing by 1,000 here. So that's 0.075 liters. Now I know that it was 1 molar. I'm multiplying by the 0.075. So I'm sure you don't need a calculator for this one. You're going to have the same exact answer. But now you're going to have units of moles. So now I have my kilojoules, I have my moles, and my next step will be to bring these together and to divide them. So that's negative 2.2 kilojoules divided by the amount of moles that produced that much energy, or took in that much energy depending on what your reaction is. So for our answer here, we have negative 29. That's kilojoules per mole. So let's think about what this number is actually telling us. First of all, it's a negative value for our delta H or Q of the system. So that means that the system is losing energy, which makes sense. If it's losing energy, it has to go somewhere. That must be why the temperature of the water is going up. So the energy is going from the system into the water. Now, if our process here is exothermic, then we have to figure out which side of the equation it belongs on. So should it be the left or the right? Exothermic means heat is going outwards. It's coming out at the end. So that means that it should be on the right side of our equation. So plus 29 kilojoules on the right side of our equation. Now, I know that there is a negative sign down on the bottom for the 29 kilojoules that we just calculated. You would not put a negative sign in here, in the actual balanced equation, because that would be kind of like a double negative. Like you have a negative amount of energy coming out at the end. So the way we want to write it is that it is a plus 29 kilojoules at the end of the reaction. If I was going back to the way that you would format it on the previous slide, then I would keep the negative sign and have it off to the side. All right, that type of problem you would be very unlikely to actually see on the quiz, at least if it's not a bonus or maybe you see one question like that, because there's a lot to it. It's not a particularly difficult problem. But you have to do Q equals MC delta T. You have to remember how to write a balanced equation. You have to know how to convert to moles. So there's lots of moving parts going into that. What you would more likely see is thermochemical stoichiometry like what we have here. So in stoichiometry, you're always given one number, and you would write that down and then convert it. So that's what we're doing here. We're trying to convert this kilojoules to some other unit. We're trying to get to grams. Now, we're able to do this through a series of equivalencies that we know. Kilojoules can be related to another unit, and that would be moles. If you look in this balanced equation, we have 129 kilojoules for the mole values, which are our coefficients, which would be out in front of each of these compounds. Now here we're talking about sodium hydrogen carbonate, which is NaHCO3. So the moles of NaHCO3 should go right here on this line, which in this instance is a 2. Now this tends to confuse some students because for the most part, you're used to making the moles a 1 when you're going to other things, like grams. If you're going with molar mass, it would be 1 mole equals the molar mass from the periodic table. 1 mole is equal to 22.4 liters if you're talking about gaseous volume. And 1 mole is equal to 6.022 times 10 to the 23rd if you're converting to particles. Here, because this is in the balanced equation, we're going to say that it is 2 moles of the baking soda for the 129 kilojoules. Alright, once we've gone and canceled out our kilojoules and gotten to moles, now this is just like the stoichiometry unit. I'm canceling out moles of NaHCO3 to get to the unit I want, which in this case is grams. 1 mole is equal to the molar mass from the periodic table, so we have 84.01. So from here you multiply and divide across, you end up with 504 grams of baking soda. For the most part, when you're working on these types of problems, they're going to end up being two-step conversions. If you're going between kilojoules and grams or grams to kilojoules. If you ended up with moles, where you're either starting with moles or ending with moles in the end, then it would only be a one-step problem. You're not going to run into any examples where you have a three-step like most of stoichiometry. Alright, next up, we're doing the same type of problem, but this time we're starting with the grams and we're trying to find the kilojoules. So we're basically just running this in the opposite direction. I'm going to write out my 5.66 grams of carbon disulfide. I'm going to set up my 2 conversion factors. My first one, I'm going from grams to moles. 1 mole is equal to the mass from the periodic table, so if you add that up, it's 76.15. Then we're canceling out our moles of CS2 on our way to kilojoules for CS2. Now here, it won't necessarily be 1. I have to look at the balanced equation. There's a 1 in front of carbon, a 2 in front of the sulfur, and a 1 in front of the CS2. So this will be 1 mole of carbon disulfide, but it's a coincidence that it happens to be 1. So we do look at the balanced equation. That number does come down here when we're talking about kilojoules. The kilojoules is over here for delta H. It's 89.3. So we're going to multiply by 89.3 here, and then we're going to divide by 76.15. It's going to come out to 6.64 kilojoules. Alright, final problem for thermochemical stoichiometry. I mentioned before that you could potentially either start or end with moles, so I wanted to show an example of that as well. So we have this many moles of Fe2O3, and we're trying to get to kilojoules. Moles and kilojoules can be related directly, so that's just going to be one step. Alright, so from our balanced equation, it looks like Fe2O3 does not have a coefficient, so that's an implied 1. The kilojoules are 26.3. And from here, I'm going to multiply and divide across, and I end up with 89.4. Now this problem could be changed in any number of ways. So let's say I still have 3.40 moles, but this time I'm talking about carbon monoxide. The kilojoules is not going to change because that's from the balanced equation. It's the same for each of the different compounds which happens to be here. But now if I'm talking about moles of carbon monoxide, I'm going to have a different value here. So carbon monoxide would have 1, so I would have a 3 here. So I'm going to end up with a different answer because it's a different compound. Alright, next up we're going to talk about the heat of fusion and the heat of solidification. So all solids absorb heat as they melt to become liquids. We know based on prior knowledge from this class that you're in the process of breaking intermolecular forces as you add heat to a solid substance. The molar heat of fusion of a substance is the heat absorbed by 1 mole of that substance as it's converted from a solid to a liquid. And the symbol is delta H of FUS. The molar heat of solidification is the amount that is released by 1 mole of that substance as it's converted from liquid to solid. So we're basically just going in the opposite direction. Now, this part right here should make sense to you based on the rest of this unit. We know that based on the law of conservation of energy, energy is never created or destroyed, simply transferred from one form to another. The fact that we can flip the sign when we're talking about calorimetry is because of that law, and that's essentially what we're doing here. If we're talking about water specifically, going from H2O solid to H2O liquid, you would have to absorb 6.01 kilojoules per mole. Well, if you're going in just the opposite direction, you're going from a liquid to a solid, that means that you would release the same exact amount of energy. So this doesn't have to specifically be for water, it could be any substance. But the point is that the heat of fusion and the heat of solidification are going to be equal and opposite in sign. The same could be said if you were going to go through the evaporation and condensation process. If you're going from H2O liquid to H2O gas, and then H2O gas back to H2O liquid, they wouldn't necessarily be the 6.01 that we see here, but they would be the same as each other. Alright, the final part of thermochemistry that we're going to be talking about is Hess's law of summation, which states that if two or more thermochemical equations can be added together in some way to give you the final equation you're looking for, then the heats of reaction can also just be added to each other. Now, this is going to be a lot like a puzzle, where sometimes you can just kind of fit the pieces together and it comes out exactly the way that you want it to, and other times you might have to kind of rotate or finagle it to get it to be the way that you want it to. So let's take a look at an example of this. We have one chemical reaction where carbon is being added to half of an O2 molecule to make carbon monoxide. Then we have carbon monoxide plus half of an oxygen molecule to make carbon dioxide, and we have the delta H values for either one. But let's say that I don't want either of these reactions. I actually want to know what delta H would be for this one, which is slightly different. If I can add these together in a way to make this reaction, then I could also add these two numbers. So let's check to see if that works. Carbon is not connected to anything else on here. There's no other carbons that could potentially add to it or cancel out, so I'm just going to bring that straight through to the bottom. So I have carbon solid. Here I have half of an oxygen plus half of an oxygen. That would be a whole oxygen, so plus O2 gas. I have carbon monoxide on the left side of this equation and carbon monoxide on the right side of that equation. That means that they're going to cancel out, so that they will not be present on either side. Then on the right side, I only have carbon dioxide left. CO2 gas. If you check over here, that's exactly what I was supposed to get. So that means that I don't have to do any little tricks, which I'll show you on the next slide. I can simply add these two delta H values. And when you add these two together, you end up with a negative 393.5 kilojoules. Now what's great about this is even though you didn't do this particular experiment, you didn't actually add the carbon with oxygen to make carbon dioxide, you know exactly how much energy would be coming off of that based on the energy that is stored in the bonds. So it allows chemists to kind of predict what would happen were they going to do a reaction. Alright, our next example is going to be a little bit trickier. So the way that these will always be formatted is that I'll kind of give you what you're shooting for on the bottom, and then the puzzle pieces that you have to work with up on top. So what I typically do is I check to see if everything is already in the spot that it's supposed to be in. So for example, I know that I want CuCl2 to be on the left side of this arrow. Alright, in this equation right here, there is no CuCl2. In the top equation, there is a CuCl2, but it's on the wrong side of the arrow. Now there is a way that we could fix that. So I'm going to rewrite the top equation, CuCl2 solid is going to make Cus plus Cl2G. Now I'm allowed to switch the order of these two to make reactants products and products reactants, as long as I also flip the sign of delta H. So now instead of having a negative 206 kilojoules, it's going to be a positive 206 kilojoules. And now since I've replaced this equation, I'm just no longer going to use it. Let's see if there's anything else that I have to change. I'm supposed to have CuCl on the right side. It looks like that's already on the right side. I'm supposed to have a copper which is on the left. I do have a copper on the left here. I also have one on the right. It looks like that should be set up completely. Now I want to see whatever the net change is. So I have 2 coppers on the left side of the arrow and only 1 on the right. So it's going to cancel out, but not completely. So I'm left with 1 copper, and that's going to come down to the bottom, Cus. All right, I also have my Cl2 and a Cl2 on the right side. So they're going to cancel out completely. All right, next I have CuCl2, solid, and it doesn't have anything else to cancel out with. These two do look very similar, but CuCl2 and CuCl are different, just like H2O and H2O2 would be different. So different formulas, different numbers of atoms. On the right side, I have 2 CuCl, and that's solid. And I just double checked to make sure it's the same as down here. This order is currently reversed, but that doesn't matter. It's like saying 1 plus 2 or 2 plus 1. It's the same exact thing. So this did come out the way that we want it to. So now we just have to add our 2 answers here. So we have 206 and a negative 136. That's going to be delta H is equal to a positive 70 kilojoules. Now there are other little tricks that you could do to make it work out the way that you want it to. For the most part, they'll either stay the way they are or you might have to flip them. Sometimes you may have to double one of the equations. So for example, if I needed more coppers, chlorines, and copper chlorides over here, I could double each of my coefficients as long as I also double the delta H value over here. By the same token, if I needed less, maybe I have the coefficients for each of them, and I'm allowed to do that as long as I have the delta H value. So it's not really possible to necessarily show you all the different possibilities that are out there right now, but it is pretty easy to figure it out. You just gotta play around with it like a puzzle until you get it to look the way that you want it to. And we'll be doing a lot of practice in class with that. All right, so that concludes our unit on thermochemistry. The unit for this in CK12 was 12.1 to 12.17. There's a couple videos that we did not watch in class that will probably be helpful to you. If you're still confused about the process of calorimetry and how it works, that was the styrofoam cup with the water. There's a really cool crash course episode on that with Hank Green. So that's on our YouTube channel, which you could watch. There's the chemistry of cold packs. This is one of the animated TED Ed videos. So it doesn't really go through any calculations, but it is entertaining and it's a nice little review of a lot of what we covered. Food calorimetry common mistakes, that was actually a homework assignment, so that was assigned through Kia. You should have watched that at this point. If you haven't already done so, please do. And make sure that you're comfortable with what was in that video because you could see something from that on your quiz. Finally, if you are still having some trouble with Hess's Law, there's a tutorial video which is specifically geared towards that, which is on our YouTube channel as well, so you can check that out. Otherwise, if you missed any of the notes and you are still not comfortable with what you saw in the video, make sure that you come in for extra help at some point before the thermochemistry quiz.